I'm going to run through some of the problems from your problem set in this video. You'll notice this video has IR and NMR in it, and that is because we will typically use both data from both of these instruments when we are characterizing molecules in lab. So make sure you review the numbers that you should know for the typical IR stretching frequencies and NMR chemical shifts before you move on to the rest of the problems in this problem set. I can help you with this first IR problem if you'd like a little bit of review. We're going we could start a couple of ways. We could just sort of think about the stretches that we expect for each of these molecules, and then maybe we can take a look at the spectra. So we expect only a OH stretching frequency for that first alcohol. For this molecule, we have an alkene functionality, so there should be a carbon-carbon double bond stretch around 1600 wave number. There should be a carbonyl stretching frequency around 1715 wave number. Those are just approximate values. Now we can point out that there should be, for the alkene, we can think about the CHs. We will have the CH stretching frequency just above 3000 for that sp2CH. We will have lots and lots of sp3. There are lots and lots of sp3CHs, so we also expect to see some of that CH stretch just below 3000 for the sp3CHs. And then which is just a embarrassment of riches here. We have the aldehyde stretching frequency. So we expect to see the twin peaks here with stretches at around 2800 or 2850 and 2750. So we'll twin peaks for the aldehyde there. Now the rest of the molecules are pretty boring. After that discussion about the CH stretches, you might go back to the first alcohol and say you only expect these stretches to be just below 3000 because all we have in this molecule is sp3 carbons and sp3 carbon hydrogen bonds. Okay, this molecule, you'll expect the stretching frequency around 1720 from this ketone, and that's really all there is, and then you just have sp3 CHs. So again, the stretching frequency will be just below 3000 wave number. And then for the last molecule, we can see we have another alkene, so we will have sp2 CH stretches just above 3000 in addition to the sp3 CH stretching frequency just below 3000 wave number. And maybe even more helpful, we'll have the CC stretch from the alkene around 1600 wave number. And if you don't have those numbers memorized, well, I mean, that's why you just did this exercise. Now that we've completed that initial analysis, please take a look at these three spectra and try on your own to assign them to one of these four molecules. Let's take a look. Let's start with the easiest one. The easiest one is molecule C, spectrum C. So we have an OH. So I'm scanning from left to right. I have an OH. Then when we get to 3000 here, we can see that the entire CH peak is to the right of 3000. So that means that they're just sp3 CHs. And then there's nothing. There's no triple bonds. There's no double bonds. Right? And then there's not another peak until we get almost all the way to 1400. So which of these three molecules only has a hydroxyl group? Yeah, this one. So spectrum C corresponds to this alcohol. Let's try spectrum B now. So for spectrum B, scanning from left to right, we see there's no OH. We come up to the CH peak and we just want to check and see where it is relative to 3000. And it's all to the right of 3000. So that suggests to me that there are only sp3 CH bonds in whatever molecule this is. Keep going, there's no triple bonds, but I do see this strong peak. Looks like it's around 1700 or so, 1720, perhaps. But it's definitely in the correct place for a carbonyl. And then I don't see anything else. There's no alkene, and then we don't know how to interpret the fingerprint region. So let's see, which of the molecules corresponds to this? A carbonyl, all sp3 hydrogens, and really nothing else. Well, that would be this molecule. I know we can't see anything in here anymore, but that would be this molecule. You know, this one, the aldehyde, it would have the aldehyde CH, it would have sp2 CHs, it would have all kinds of things that we do not observe in spectrum B. So spectrum B is the ketone. Oops. All right, spectrum A. Spectrum A is nice and exciting. We have this peak here. What is that? Well, that is the sp2 CH stretch. Yeah, it isn't always so distinct, right? And then we have the sp3 CHs. And then really nothing. There's no triple bonds. There are no double bonds. Well, is there a double bond? What's this? Yeah, that is a double bond. There's no carbonyl though, so there's nothing between 18 and 1700, so there's no carbonyl, but there is a CC double bond stretch. That suggests that this spectrum corresponds to this alkene. All right, we've assigned spectrums A, B, and C now. Now that we have refreshed our memories on IR, let's get back to NMR. So we have this molecule and its NMR spectrum, and we want to assign the NMR peaks. So we're going to do that now. We can see that there are 3 peaks, and then this is the reference. So the signal at 0, this is that tetramethylsilane reference, so we're not going to worry about that. We can see that the relative integrations are going to tell us the relative number of protons in each group. So you might, if you add up the molecular formula of this compound, you will get C6H12, but you can see that there's only 6H in the spectrum. Well, that's because it's symmetrical. So the absolute numbers will be 2, 4, and 6, but the relative ratio 2, 4, 6 is 1, 2, 3. Remember, the NMR instrument itself does not know how many protons are in your molecule total. It's just taking a ratio of the area under the 3 curves for these signals. So these protons are HA, and they show up here. There are 2 protons in this group. And if we could zoom in on this peak, we would see that it looks like this. How would you describe this splitting pattern of that peak? Yes, it is a triplet. And it is a triplet because HA has 2 neighbors, 2 chemically equivalent neighbors. And those neighbors are HB. Now this is confusing because each HA has 2 neighbors. So those 2 neighbors plus 1, that's the n plus 1 rule, gives you the 3 lines that make up the triplet, and that 1 to 2 to 1 relative integration of those 3 lines. Excellent. Don't be confused because I know there are 4 HB overall, but each HA only sees 2 of them. So 3 lines. The chemical shift is at 5.5 ppm. That's pretty typical of a vinyl proton. So how does she know? Well, because she memorized it, but also because I didn't skip this step here, and vinyl was here at 5 ppm. Vinyl directly attached to the 2 carbons of the alkene, or one of the 2 carbons of the alkene. Where is HB in the spectrum? Well, HB is right here. There are 4 hydrogens in that group. Now, you might wonder, oh, chemical shift at 2, you told me chemical shift at 2 is adjacent to a ketone or carbonyl. Yes, I mean, often that is what that does represent what shows up at 2. However, in this case, you now have another example of a type of proton that shows up at 2, and that would be the allylic hydrogen. So allylic means adjacent to a double bond. That double bond de-shields them a little bit, and that's why they show up a little bit more downfield than a typical alkane. They're allylic, they're adjacent to a double bond. So they show up at 2, and we won't worry about their splitting. We'll look at splitting more in a little bit. And then finally, we have 3 protons here. So they integrated to 3 because that was the relative number, but we said that we needed to multiply everything by 2. So that's actually 6 H's, and that that signal represents these methyl groups. They are HC. All right. So this is actually 6 H's. And we can think about their splitting if you want. Each of these each group of 3 hydrogens, look at the adjacent carbon. Each of those groups has 2 equivalent neighbors, so you do expect it to be a triplet. And if you could zoom in, you would see that. And I'll be real with you, I skipped this splitting for this signal because it's more complicated and I don't want to talk about it right now, but I will in a minute or 2. Okay, awesome. Everybody's good? Where the 1 to 2 to 3 you need to multiply by 2 to get 2 to 4 to 6, because 2, 4, 6 adds up to 12, the number of hydrogens actually in the molecule. So let's try again. Let's try to assign the protons in this NMR spectrum. Let's begin with the easier signals and work up to the harder signals. So I think that the easiest one is that the OH is its own group. Now I've told you, you don't always see that in that OH signal in the NMR. You will see it for this particular OH. You just happen to. Here it is. That's the OH. So HA. I can tell you that phenol hydroxyls often show up around 5.5. Okay, because it's different than just a normal old alcohol, where that's an alkyl group, an sp3 carbon, where this shows up around 2. 2 ppm. Maybe a little bit lower, but it's up around 2. It can move around. Okay, so we do see the OH. There it is, 1H OH. All right. What else is easy? The 3 H's, that's easy. That would be this methyl group, so we'll call that HB. Okay. Awesome. Let's keep going. Let's take a look at the aromatic protons. So we have 3 hydrogens, all around 7. They're a little bit less than 7, but those are only options. We know the aromatic protons show up around 7. So these 3 protons are represented by that group. So we'll call them C, D, and E. They are all chemically inequivalent, and they show up there. Let's look for these 2 protons. This is exciting. These are benzylic, which means adjacent to a benzene ring, a phenyl ring. So benzylic, and allylic. We just talked about what allylic means. Allylic means adjacent to a double bond. Wow. So being just allylic moved these protons, HB, to 2 from where they would normally show up at 1. I wonder what being allylic and benzylic will do. Yeah, wow. These protons, let's call them HF, they show up all the way at almost to 3.5. That's crazy. That could be really confusing because when we think about 3.5, we might think about amines and alcohols. So this would be the proton bonded to an alcohol or an ether. And this would be the proton bonded to the carbon that has an amine functional group. Not the OH or the NH, but the CH. So yeah, our allylic and benzylic one was all the way down here. Whoa, that would surprise us probably, huh? We got to roll with it. Real data or real problems? I don't know where to go from there, but real data, we need to just think and be critical. So our last peaks are this one and this one. So let's do the 1H first. So this 1H here, that is Hg. And the 2H, this is overlapping peaks. So we're going to call this, you're going to love it, HH and HI. HH here and HI, they are technically diastereotopic. So they should have different signals. Do the substitution test. They are not chemically equivalent. And if you don't know any of the words that I'm saying, you probably did not do the guided inquiry questions, or you need to go back and do your reading and do your guided inquiry questions so you know what I'm talking about. So they should have different signals, but those signals are just overlapping. They're overlapping here. That's fine. They're just really similar. So they're overlapping, and those protons H and HH and HI, they're right there. Well, that was a fun one. Let's keep going. So now we're going to look at the splitting patterns and try to understand what's going on. So first of all, we have 3 signals in this spectrum, and that's because there are 3 groups of protons. Okay, we'll start with the easy ones and move on to the hard ones. So let's take a look at HC. So HC is furthest away from this electron withdrawing group, the cyano group, the nitrile group. So HC is down here. And if we could zoom in on HC, what do you think it would look like? Yes, it would look like a triplet. And that is because it has 2 neighbors. There are 3 lines, subtract 1, and that gives you the number of neighbors. Awesome. So what are the two neighbors for HC? Well, here is HC and HB. There's 2 protons in that group. And so those are its 2 neighbors. So these protons split the signal for HC into a triplet, 3 lines. Good. Let's take a look then at, let's skip to HA. HA is going to be the furthest downfield because it is the closest to that electron withdrawing group. And HA will also be split into a triplet because HA has these 2 neighbors. So N equals 2, and then N plus 1 equals 3, which equals the splitting pattern for the signal, just like we discussed with our guided inquiry questions. So HA will look like this. It will be a triplet. It has 2 neighbors. Wow, HB is really coupling. That's what it means to split another set of protons. It is coupling to lots of different things. So HB, it has 3 neighbors. And what did three neighbors do? Yeah, three neighbors would split HB into a quartet. HB also has, though, these two neighbors. And what do these two neighbors do? Well, they would split it into a triplet. So what happens? Well, what happens is kind of complicated, but technically you would have a triplet of quartets or a quartet of triplets, depending on some complicated stuff. Really, it's just a mess. What you have is a multiplet. Multiplet just means unspecified. It doesn't fit one of those nice patterns that we discussed. So triplet of quartets. If you actually saw a triplet of quartets, it would be the most amazing thing that ever happened to you. I've seen it like twice in real life. It would look like this. So the quartet, it was the four lines, and then each of these four lines is split into a triplet. Doesn't that look amazing? Hopefully everybody goes on to graduate school, gets to see fun stuff like that. It's a multiplet for us. You might see somewhere where somebody says, oh, that proton has five neighbors. 5 plus 1 is 6. It'll be a sextet. No, that person is wrong. It has two groups of chemically inequivalent neighbors. So technically, it would be split into a triplet by one, a quartet by the other. It's going to be complicated, and it's probably going to just be called a multiplet. When you can't tell what's going on, it's a multiplet. And yes, that's legal. I'm the boss. All right, HB. All right, let's keep going here. This is fun. Let's take a look at this NMR of styrene. Styrene is this alkene attached, the vinyl group attached to a phenyl group. And we are just going to take a look at the vinyl protons. Okay, so the signals that correspond to these protons. And the point of this exercise is to show you that the amount of splitting that's occurring between two protons, and this is called their coupling. It can help you figure out, it can help you distinguish between HA and HB. Okay, so HA and HB, they're going to couple each other because they're different, right? They're diastereotopic. If you did the substitution test, you would see that they make diastereomers, and so they are different. They have different signals in the NMR. Awesome. And so they couple each other, and they couple each other with a coupling constant. This just means amount of splitting. And I'm not going to go into any more details in this class. I would love to, but we can't. So this coupling constant, just represented by J, it just means the amount of splitting. So we're going to look at big and small, and we're not going to worry about hertz. Just going to look at big and small. So for this geminal relationship, these two protons here have a geminal relationship. There's a really small coupling. So the HA and HB, like this teeny tiny coupling here, that is their geminal coupling. That's how they couple each other. And I'm not sure that I was very clear. One of these signals belongs to HA and one of them belongs to HB. And the point of this exercise is to figure out which is which. So the teeny tiny geminal coupling, that's just HA and HB coupling to each other. But then you can see there's a much bigger coupling. So there's this coupling and there's this coupling as well. These are really good examples of where I said things are complicated. So HA, it's split into a doublet by HB, that's this tiny doublet, and into a doublet by this proton, the other vinyl proton. And that's this bigger doublet that we're seeing here. So let's figure that out. So HA, it is cis to the other vinyl proton. Cis coupling is smaller. Cis coupling is smaller than the trans coupling. Look at the trans. Okay, so it's smaller. So we have tiny for geminal, smaller than trans for cis. So we can see, oh, okay, this is smaller than this one. So what does that mean? That means that this signal corresponds to HA and this signal corresponds to HB. This bigger coupling here, this bigger distance between those two lines, that is due to this trans coupling between HB and the other vinyl proton. Let's get to the real fun. And the real fun is to use IR and NMR data to solve for the structure of unknown compounds. We identify a new compound, compound X, and mass spectroscopy, which we may or may not learn about next semester, suggests a molecular formula of C9H12O. And the following IR and proton NMR are recorded. So let's analyze them. Looking from left to right, we see this peak. This is an OH. Next, we have the CH stretches. I can draw my magic line at 3000. I see that there are stretches above and below. So the above 3000, those are sp2ch stretches, and below 3000, those are sp3ch stretches. So I have both kinds of carbon-hydrogen bonds in this molecule. There are no triple bonds in the triple bond region. There are no carbonyl stretches in the carbonyl region. I do see something interesting though, and that's these little bumps here. These little bumps, there's something called an overtone, and I'm not going to explain what that means, but often when you see those four little bumps, those four overtones, you might have a benzene ring. So since I think we might have a benzene ring, let's look and see. Oh, look at that. Those are the two CC double bond stretching frequencies we often see for aromatic rings. This right here is an aromatic CH bend. So the CH bonds can bend out of plane, meaning imagine pulling this hydrogen towards yourself. Okay, so that's what that is. It's a CH bend. All right, so there's definitely an aromatic ring in this compound. Aromatic ring and an OH. That's what I get out of this, really. And then I get out, there's got to be some alkanes as well, some sp3 carbons. Cool. Now let's take a look at the NMR. Yeah, the NMR immediately confirms what I thought from the IR. Here, there's 5 hydrogens, right around 7. So that will be a mono-substituted benzene ring. I know that aromatic CH stretches are around 7. And if there's one substituent, then there are 5 positions left for hydrogen. So 5H. Excellent. What else do we have here? Okay, we have 4 more signals. Let's go back and look at the formula. The formula was C9H12O. We know there's an OH. Oh, I bet that this right here is the OH. And what else do we have? Well, we have 2 hydrogens, and these 2 hydrogens are a quartet, right? They're a quartet. And then there are 3 hydrogens that are a triplet. A triplet means that those 3 hydrogens have 2 neighbors. A quartet means that these 2 hydrogens have 3 neighbors. 2 hydrogens with 3 neighbors. 3 hydrogens with 2 neighbors. Hey, I bet they're connected. Yes. Okay, CH2, CH3. I bet they're connected to each other. So this signal for these protons, this signal for these protons, right? And The integrations, these are the integrations. Those are telling me the number of protons in each group. Now we have one signal left. That's this signal right here. It's 1H. So we have CH. It is a triplet. So you can see, or you can glean, it has two neighbors. Cool. Let's see if we have everything. We do have 9 carbons, 6, 8, 9. We have the O and we have all 12 H's. Now we need to connect the dots here. So let's see if we can put together the structure of this molecule. Oh no, I gave it away sort of. All right, so start with the benzene ring. We also have the ethyl group. Okay, and we have the OH, we have the CH. We need to start putting some things together. So first of all, we're not going to be able to connect the benzene to the ethyl because then like there's nowhere to put anything else. So I bet that the benzene is connected to that CH. Okay, and then what else? So now we've got that. And now let's try to put the ethyl group. Let's move that over there and connect it to that carbon as well because there's an open spot. And let's put the OH over there as well. And let's just see if this makes sense. We don't really have a lot of other options for connecting the dots here. Okay, we would have 5H at 7 for the aromatic protons. Check. For this, we would have 1H. Now this 1H, what would you expect for the chemical shift? Well, I would expect it to be pretty downfield for an sp3 carbon because that proton is benzylic. It's adjacent to the ring, and it's an alcohol. It's the alpha carbon of an alcohol. So that gets you 4 ppm alone. So you can see, yeah, it is pretty downfield. It's almost at 4.5 ppm. Now, would you expect it to be a triplet? Yes, you would, because it has these two neighbors. All right, so what you do to figure out the neighbors is you look at, this is the hydrogen we're interested in. This is the carbon it's on. Go out 1 carbon more. So this carbon has 2 protons on it, and there's the n+1 rule. N+1 is the number of lines that this signal will be split into. 2 plus 1 is 3, and so we do see 3 lines. Now, you have to look at the other adjacent carbon atom as well. There's no protons on there, so it won't split this signal at all. And then the OH doesn't usually split, but that is probably why this signal is so broad, because it's next to the OH as well. But we do expect a triplet for this because it has 2 chemically equivalent neighbors. So expect a triplet, and that's what we see. Good, so far so good, right? So ppms are consistent with our expectations, and then also we expected a triplet. From here, let's look at this CH2 group. This CH2 would be split into a quartet by these 3 neighbors. And, oops, well, this is a neighbor too. So what's going on with that? Well, this would split it into a doublet because it's 1 neighbor. So you might have a doublet of quartets. It could look like this. Now it'd be maybe really hard to see. It looks really similar to just a normal quartet, right? And if we could zoom in here, I mean, you can see like something funny is going on at the peaks of the quartet. So I'm pretty comfortable with this. I think it's just fine. And then finally, we have the CH3. This should be a triplet because of its neighbors, and it is. You would also expect that CH3 to be the furthest down upfield because this CH3 is closest to 0, because this CH3 is furthest away from the hydroxyl and from the benzene ring. So everything makes sense. We checked splittings. We checked chemical shift, the ppm values. We checked the molecular formula. And we checked the integrations. And we're good. Let's try again. You just try this yourself before you listen to me explain it. You'll get much more out of it. Ooh, I forgot to show you something on the previous page. I'll show you now. So you should calculate your index of hydrogen deficiency from the molecular formulas. That can really help you. So here we have an index of hydrogen deficiency of 5. In the previous example, we had an index of hydrogen deficiency of 4. The index of hydrogen deficiency represents the total number of pi bonds and rings in the molecule. So in the previous example, there were 4 total pi bonds or rings. So let's look at our answer and make sure. So 1, 2, 3 pi bonds plus 1 ring, 4. So the index of hydrogen deficiency matched up with our structure. This time there'll be 5, and when there is such a high number for the index of hydrogen efficiency, you really should just suspect a benzene ring just from the outset, since it itself, as you just saw in the previous example, has an index of hydrogen deficiency of 4. Let's see what we have here. Well, we have no OH this time. Draw our magic line at 3000. We can see that we have sp3CH and sp2CHs. There are no triple bonds. Ooh, I see the bumps again. This makes me suspect benzene, those overtones. There is this time a carbonyl, this nice strong peak right around 1700 wave numbers. And then, ooh, all right, we got some double bonds here. And then that's most of the useful information from this spectrum. Probably just this one. Okay. So from the IR spectrum, what functional groups are definitely present? Well, a carbonyl and an alkene for sure. What functional groups are definitely absent? I don't see a hydroxyl. I don't see any triple bonds. Here's the proton NMR spectrum. Yes, immediately this jumps out at me. This signal for 5 protons at 7, that is an aromatic ring. It's a mono-substituted aromatic ring because one substituent leaves 5 positions for hydrogens. Oh, and these are beautiful. Look at these. So we have 2 CH2 groups and they're triplets. Triplets, right? So if these are triplets, they each have 2 neighbors. 2 equivalent protons on a neighboring carbon. 2 hydrogens with 2 neighbors. 2 hydrogens with 2 neighbors. Who thinks they're connected? Indeed, they are. This is so fun. And if you don't think it's fun, try to trick yourself into thinking it's fun because it's much easier to do when it feels fun. Finally, we have 3 hydrogens. That is probably a methyl group. And those 3 hydrogens are a singlet, so they have no neighbors. They're going to be isolated. I also notice, that signal is at 2. And what did we figure out from the IR? Yeah, we figured out there was a carbonyl. And a methyl ketone would show up right at 2, and it would be a singlet because this carbon, the neighboring carbon, the carbonyl carbon, it has no hydrogens on it. So that means these protons that correspond to this signal would have no neighbors. Super, because that's what we see. So let's go with that. Let's see what we have so far if we have all of the atoms that we're supposed to have. So C10H12O. 6, 8, 9, 10 carbons. Awesome. We have 10 carbons and we have 12 hydrogens. We have our oxygen. We're good to go now. Let's connect the dots. So then we have this methyl ketone piece, and then we have the CH2, and we have the ring. So there's really only one way to connect all of these, and that is like this. So the CH2 should be connected to the carbonyl, and then you have the benzene ring. So connecting it that way, all of the integrations and splitting patterns are correct. We can just double check chemical shifts. So we do expect this to be around, the methyl to be around 2 ppm. Again, it would correspond to 3 hydrogens, and it would be a singlet because there are no neighbors. Next, here, so this is also alpha to a carbonyl. The CH2 group is also alpha. So maybe we expect it to be around 2 ppm. But it's pretty close to this benzene ring too. It's not benzylic, but it's relatively close to that benzene ring. So that pulls it downfield as well. So that's why it's showing up a little bit closer to 3. But that signal corresponds to those 2 hydrogens. Then we have this set of protons. These 2 hydrogens, they're benzylic. And so benzylic, and they're almost to 3 ppm. So this being benzylic really shifts those protons downfield. Again, that was a tricky one because when we didn't learn about benzylic when we first learned about chemical shifts. So it's good to know being adjacent to the benzene ring can pull the signal downfield towards 10. All right, where are we now? Yeah, we're good. And then these 5 protons correspond to those 5. Okay, I like this. Good job. But we need to assign the peaks. So let's do our ABC. So A, B, C. And these are all different, but we'll just call them D because we're not too worried about it. So we have A, B, C. They're not all different, but these 2 are equivalent, these 2 are equivalent, and this one is its own. But they're all showing up together, so we'll just call them D. Okay, good job, guys. Let's try another one. I will do 2 more for you. But you have to promise that you're going to do this yourself first. Great, so you fulfilled that promise, right? So there's no OH. Then we're going to draw a line at 3000. It does look like there are sp2CHs and sp3CHs. That is confirmed, or some evidence is added to that with this weird peak that looks like that's around 1600, so I think it's an alkene. So definitely present, alkene, double bond. Definitely absent, there's no OH, there's no triple bonds, there's no carbonyl. Oh, this looks interesting, though. That looks like a CO single bond. And there is an oxygen in this molecule. You guys want to go ahead and do the IHD? Yeah, so it was the number of carbons minus 1/2 of the hydrogens plus one. Oxygen doesn't count for the IHD, so we're not worried about it. So that would be 4 minus 1/2 of 8 plus 1, which gives us a 1. All right, so there's going to be 1 pi bond or ring. Here's the proton NMR. Oh, this one's fun. Okay, here's the proton NMR. I want to show you a pattern that can be helpful for you to recognize. There's 2H, and those 2H are a quartet. There's 3H, and that 3H are a triplet. So why is that important? Okay, well, triplet means that they have 2 neighbors. Quartet means that it has 3 neighbors. So 2H with 3 neighbors, 3 hydrogens with 2 neighbors. They're going to be coupled. They're connected to each other. So we're sure we have an ethyl group. Now let's just take a step back for a moment. There's only 4 carbons in this molecule, and you also know from the IR that there is an alkene. So we also will have this vinyl group. So 4 carbons, 1, 2, 3, 4. So, I mean, we're done, really. We just have to connect them with an oxygen. Wow, I mean, that seems too easy, right? Yeah, it's a lot harder if you don't think about it that way. Let's just confirm what we just came up with. So check out these 3 hydrogens we haven't even talked about yet. I think all of them can be confusing because when you think about an alkene, you're thinking about 5 ppm, right? But this is not just an alkene. Like the alkene is connected to oxygen, and being connected to oxygen kind of messes with the chemical shifts a little bit in a couple of ways. So first of all, oxygen is electronegative. So it's going to be pulling electron density towards itself, right? So that de-shields this proton. So we'll call this one HA. So here's HA. It is de-shielded. But oxygen is also donating electrons in the pi system. And we can draw a resonance structure. So it looks like this. Or you can see, whoa, these hydrogens are shielded. There's extra electrons there. And yep, that's what you see. Those two hydrogens, they're right here. They're further upfield, shielded than usual. So it makes sense, but when you first look at it, I think it's really tough because it's not, those chemical shifts are just not what you expect. So here we have HB and HC, and you don't have to worry about which one is which, though you do know. So let's actually do it, because remember what we talked about, and it was probably pretty confusing earlier. HC is cis to HA, but HB is trans to HA. Trans coupling constants are larger. So trans couple more means they split more. So you have a bigger difference between the peaks. So look at that. So there's a bigger split there for that signal. So that is actually HB. That's cool. I'll show you where we get that knowledge from. It was probably a while ago. And this one's HC with that smaller cis coupling constant. I am referring to this slide right here. Okay. All right, so it's good. And then we can just check one more thing. We can do two more things. We'll check the chemical shifts. So this chemical shift we expect to be around 4 ppm, and it is. It's right here, right around 4 ppm. We can call those HD and just label it on our spectrum. So this would be D, and we'll call this E. Okay. So great, and we expect that to be closer to 1 because it's alkane-ish. All right, very good. And the IHD works too, right? There's just the 1 pi bond. So everything is nice and consistent. Like putting together the pieces of a puzzle. Really fun once you get the hang of it. All right, try this one yourself. And I think this is the last one I'm going to do with you. Yeah, the rest you're going to do on your own. So there are no OHs. Draw your magic line at 3000. It looks like we have all sp3CHs. So maybe you want to go check with your index of hydrogen deficiency. Let's do IHC. This is fun because we have to keep in mind of the halogen here, and I can never remember the formula. So I believe you count the halogens with the hydrogen. So 1/2 H plus X plus 1. And we're just going to find out on the fly because that's how we roll. You can memorize this equation or look it up. So that begs the question, why haven't I? My brain is just funny. Cool, so we should get 5 minus 1/2 of 10 plus 1 gives us 1. And that is correct. Because I know the answer. Okay, awesome. So which functional groups are definitely present? We're not quite done yet. We see there's no triple bonds. They come around 2200. But there is this nice peak right here around 1720-ish. And that is the carbonyl. So carbonyl is definitely present. And I don't see really much else. There's no OH. We said there were no triple bonds. There's no CC double bond. There's nothing here around 1600. So here's the proton NMR spectrum. Well, let's take a look at it. Let's rewrite the formula. So C5H9O2Br. All right, what jumps out at you? Well, there's two methyl groups, right? So there's this methyl group and this methyl group. Okay, so we have a methyl. This is a triplet, and so that means it has 2 neighbors on two equivalent hydrogens on the neighboring carbon. This CH3 group is a doublet. Its signal is a doublet. So that means it has one neighbor, one neighboring hydrogen on the adjacent carbon. Okay, then we have a CH2, and it's a quartet. So the 2H, that tells me the CH2, it's a quartet. So that means it has three neighbors on the adjacent carbon. So immediately you think, okay, that one couples to this one. So they're connected. That CH2 and that CH3 are connected to one another. Another useful piece of information is look how downfield this is. I mean, it's at 4.2. So I am pretty sure that this is going to be connected to the oxygen atom because of how far downfield it is. I don't know for sure though, but I think so, right? Okay, then we have a CH. This is also really far downfield. We have a CH, and it's a quartet. It's a quartet. Sorry, I'm thinking. I've solved this problem 100 times. Just like thinking about it anyways. It's a quartet, so that means it has three neighbors, and it is going to be connected to, what do you think? Yeah, the other set of three hydrogens. Now, how do I know that? Well, that's because this set of three hydrogens was a doublet. It has one neighbor, and this is one hydrogen. Got it? It is a puzzle. You just take a deep breath and you just work through it. And sometimes you have to think about it longer, even when you solve the problem 500 times. Literally, for the past over 10 years, I've been solving this problem. Okay, so we're good now. Let's see what we have, and then we're going to put it all together. We'll just start writing it down here. So we have a CH, and that's bonded to CH3. So we'll call this one, purple. We'll call this one A. This one B. And then we have a CH3 bonded to a CH2. Okay, so these are, we'll call this C, we'll call this D. Good, and what do we still have to get in here? We still have to get the oxygen in here, two oxygens, a bromine. We only have 4 carbons. Oh yeah, we're supposed to have a carbonyl, so that's got to go in there somewhere. So where do you think the carbonyl goes? Yeah, it's going to go in between these two carbons because this carbon doesn't have any more neighbors. Carbon doesn't have any more neighbors except for the ones we've already connected it to. So we kind of isolate them. And there are 2 oxygens, so this is an ester. Yes, this is an ester. Okay, so the question becomes, which of these groups goes here and which of these groups goes here? But we got to figure that out. And we're going to use chemical shifts to figure that out. We also still have the bromine to place. But I think it should be pretty obvious now that bromine has to be on carbon A, or connected to the carbon that has proton A on it. And that's because we really don't have any other choice. It also explains why A, this signal, is so much further downfield. All right, now the only way, well, let's try both answers. And then we'll figure it out from there. Okay, so we have 2 choices. We have this choice, and we have this choice. I'm trying to find the best way to do this. I'm sorry that you're having to listen to my internal monologue more today than usual. All right, there we go. So we have these 2 choices. And I'm just going to label all the protons. So these are protons D, C, A and B. And I have an extra, I got some extra stuff here. Okay. So what do you think it is? Yeah, it's this one. This is the right structure. It cannot be this structure here cannot be that one because we would have a chemical shift of 2 ppm for signal D, and we don't. It's at 4.5 or 4.2. So it cannot be this structure because we would not get the right chemical shift. It has to be this structure. So you might say, all right, well, I mean, how do you explain this shift for proton A? Well, for proton A, it is both alpha to the carbonyl, right? Which puts it at 2 ppm, and alpha to the bromine, which apparently shifts it another 2 ppm, ending it up way down here at 4.4. So this is the correct structure. We can easily explain the chemical shifts with that structure. We cannot explain the chemical shifts that are observed with this structure. Okay, so now you have a million practice problems. Look at this. Wow, we're all getting dizzy. So many practice problems. You need to practice. The key is to be systematic, and you have a lot of information for these problems. So I'm going to lead you through what to do. So the first thing that you're going to do is calculate the IHD, and you should be checking at the end, like I should have checked here. The IHD was 1, and you see we have 1 pi bond. We're good. Okay, so you're going to check the IHD at the end. Then you're going to scan your IR. You're going to scan your IR. We're going to scan by looking for OH, looking for the different types of CHs, looking at your triple bond region, looking at the double bond region, and then you might have some significant other peaks. Like for this one, we could have recognized one of these is probably the single bond CO, which could have helped us think about an ester. Okay. This one, man, wow, these are pretty significant. Those are those out of plane bends for an arrow ring. Okay, so you're going to scan your IR. Whatever you get from your IR, write it down here. And then for your NMR spectrum, you're just going to take a really, really deep breath. There's just a number. Think about the types of information that you get from the NMR. The number of signals tells you the number of groups of protons, chemically equivalent protons. The integrations tell you the number of hydrogens in each group. You're going to use the splitting pattern to tell you how the groups are connected. And then finally, I mean, it doesn't have to be in this order, and the chemical shift tells you about the chemical environment. So if you think about the previous example, in the previous example, we didn't really use chemical shift too much until the very end, and it helped us decide between where to locate this oxygen of the ester, like which piece should it be connected to. And then while you're doing this, I mean, you can write down the pieces. So write down your pieces. Make sure that you look back. So that's what we're doing here, right? Writing down our pieces, and then we connected them. We did the same thing here. I wrote down the pieces, the ethyl and the vinyl, and then I knew there was an oxygen, and then I connected them. Same thing that I did over here. I wrote down the pieces. Remember there was a carbonyl from the IR, and then I connected them. So write down the pieces, check your molecular formula, make sure you didn't forget any pieces, check the IHD, And then you connect the dot, check your IR, right? Everything. And then you want to connect them. And then once you get a structure, just double check with your NMR. So double check with your NMR, double check your molecular formula is correct, and you'll be good. You just take it, you be very, very systematic, and you'll get the right answer. If you have any questions, please ask me.